Welcome to EDU World Space.
All right, guys, we're doing question number 90 of chapter 9 in Chemistry Essential Science. So we have this chart right here where we have our molecules, electron domain geometry, the hybridization of our central atom, and whether or not our molecule is a dipole moment. So it wants to fill the blank space in the following chart. If the molecule column is blank, find an example that fills the conditions of the rest of the row. So let's start with CO2. I'm going to draw the structure of CO2 here. I'm going to draw the structure of our molecules over here so we can better understand it. So this is our CO. That's the Lewis structure. So you have two electron domains here and here, and then you have no electron domains on our central atom. So since we have two electron domains, our electron domain geometry is linear. And since we're only forming two bonds, we're going to have sp hybridization. And generally, you can know what hybridization is based on the number of bonds you're forming. If you're forming 2, then it's sp. If you're forming 3, it's sp. It's sp2, and if you're forming 4, it's sp3. That's generally how you can do it. And we can see from our dipole moments, we have a dipole moment here and a dipole moment here. So the two dipole moments cancel out, so there is no dipole moment. Or rather, no net dipole moment. So we have a dipole moment. We have sp3 hybridization. If that's true, then our electron domain geometry is going to be tetrahedral. An example of that would be 8NH3. So this would be our NH3 structure. Since it's surrounded by 4 electron domains, it's tetrahedral electron domain geometry, and also it has an sp3 hybridization because it's surrounded by those 4 electron domains. Now, no net dipole moment, it's still going to, and still sp3 hybridization, so it's going to be tetrahedral, but instead of a polar one molecule, we're going to get nonpolar. So we get CH4. So CH4. Or you have 4 electron domains surrounding it, so it has tetrahedral geometry for its electron domains, and no lone pairs. So that means that on central atom, all the bonds are equivalent. So that means this is a nonpolar molecule. Now, for trigonoplanar, we can choose any kind of trigonoplanar dipole moment. So that means we're going to choose a trigonal plane. So that means we're going to choose a molecule that looks like ammonia, but has no lone pairs on the centron. So in this case, we're choosing BH3. Okay. Since there are 3 electron domains, you have sp2 hybridization. So for SF4, so let's draw our SF4. I'll draw it over here. So there are 4 fluorines and 6 and there's 1 sulfur, so that's going to create 28 valence electrons from the fluorine, and then 34 6 valence electrons from your sulfur, which creates 34 in total. So let's see how many electrons we have so far. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's 32. That means we have 1 lone pair here. So that means our electron domain geometry is going to be trigonal bipyramidal. I'm going to move this part down slightly. Trigonal bipyramidal. We have so for the hybridization of the central atom, it's actually a bit complicated. So the reason that you can have, so you'll notice when you look at this structure, sulfur has sulfur has 2, 4, 6, 8, 10 electrons are surrounding it, and that violates our octet rule. So the reason for this is because like if you look at your periodic table, you can see sulfur doesn't have any electrons in its d orbitals. But the reason that they believe that sulfur elements like sulfur can break the octet rule is that even though it doesn't have electrons d orbitals, doesn't use its d orbitals, it's still available if it needs it. So you would still have d orbitals involved in this interaction, but conventionally that's not the way we think when we talk about hybridization. So I would say that you would put Na here. Like it's not going to be our it's not going to be our conventional way of understanding hybridization. And because it's trigonal bipyramidal, we are going to have a dipole moment. So yes. Now for us. Now for next one. S. So for the next one, it's going to be an octahedral structure. So think about kind of octahedral structure that we would be using. And in fact, this is a bit high. Let me put that there. There. Let me try to move this up as much as I can. Trigonal bipyramidal. Just want to make sure that we're not confusing that for the next few ones. So what's going to be an octahedral structure? And octahedral structures, by definition, don't really have the octahedral structures, assuming they have the same kinds of bonds, the same atoms attached to the central atom. those are always going to be octahedral. So let's see. So let's put SF6 for an octahedral structure. Again, our bonding is going to be Na because sulfur is going to break the octet rule. Oh, so we can draw that right here. So our central sulfur atom. So the top is going to cancel out with the bottom. This is going to cancel out with this, and this is going to cancel out with this. So this creates a completely neutral structure. So, well, not neutral, non-polar. So next we got an element that is both sp2 hybridized and does have a dipole moment. So an example of this would be a trigonal planar structure. And this would be CH2O. Because if we look at this structure for our formaldehyde, we have three electron domains, and we also so there's going to be trigonal pyramidal for electron domain geometry. It's also, because we're forming three kinds of bonds, it's going to be sp2 hybridized, and also because we have the oxygen here, it's going to have a dipole moment, as opposed to BH3 here, which does not have a dipole moment. So now, for next one, we're going to have trigonal bipyramidal, and it's not going to have a dipole moment. So our molecule is going to be PF5. So let's look at this structure, trigonal bipyramidal. So you have three fluorines in the plane with one another, and one fluorine above, one below. Again, you have your phosphorus finally the octet rule like sulfur. Even though they don't use their d orbitals, they still have them, so they can break this octet rule. So our hybridization is still going to be N-A. Now for xenon, we're going to draw XF2. So xenon has 8 electrons, fluorine has 7. So 7 plus 7 plus 8, that's 22. So 1, 2, 3, 4, 5, 6, 7, 8. So that means that there are 6 electrons left. So we have to put 3 lone pairs on our xenon. And let me just move everything to the left a little. So now we're going to have a trigonal bipyramidal structure. So this is what our xenon is what's going to look like. So our lone pairs are going to have are going to be looking like this. Since we have 5 electron domains, that means we're going to be trigonal bipyramidal. So again, we're following our TET rule, so our hybridization is going to be Na. And yes, we do have, and no, we don't have a dipole moment, because if you look at this structure, although our electrons are in the plane, our electron domain geometry, the lone pairs are in the plane right here. Our fluorines are diametrically opposed to one another, so this is actually going to be a linear molecule. So this molecule would be, or rather, it's close to linear. So here, so this would not have a dipole moment, and that's how you solve these kind of things. You have to understand. To do this kind of question, you have to look at the Lewis structure. You have to be able to analyze that. You have to understand the link between hybridization, electron domain geometry, dipole moments. You have to understand all these concepts if you want to be able to solve these kind of problems.